Thanks, Loïc. And I too would like to thank Loïc for inviting me here and for writing the proposal that allowed me to come. And I'd really like to thank the National Science Foundation, GeoPRISMS, for funding this. And I think it's a fantastic opportunity to bring GeoPRISM science to universities and to talk with undergraduates and graduate students. I had an awesome time today at Pizza Lunch. Thank you so much to all the graduate students, undergraduates, and postdocs who came to that event. And I directly benefited. I'm going to get an SEM image of a harvester ant with its beard, which I'm really excited about, and just a great time. And at the Academy this morning, too, it was just for someone in a museum to go and visit another museum is an incredibly informative and interesting experience. So thanks everybody for hosting me today. It's been a great visit so far. So hopefully now I get to entertain you for a little while, and I really hope you'll interrupt and ask questions. This can be completely interactive, and I don't have any set material that I don't have any agenda to get through anything. So we can just discuss topics that interest you at will. So, volcanoes, windows to the deep. And I think there are a few basic messages I want to get across in this talk. And they're related to GeoPRISM's goals. I mean, with GeoPRISMs, we are looking at plate boundaries. We're looking at places where the Earth is, the crust of the Earth is rifting apart and new crust is being generated, or where existing crust is being destroyed. And volcanoes occur in those locations. Volcanoes are surface manifestations of the Earth's respiration. Right? So we have a lot of biologists in the room, and we are always, as biologists, focused on respiration. Volcanoes are a sign that our Earth is also breathing and respirating. And they bring material from deep in the Earth, both solid material and gases from deep in the Earth, to the surface and give us clues about what's going on deep in the Earth, which is what interests me as a scientist and why volcanoes are useful tools for me in my research, even though I, as a particular person studying volcanoes, am actually interested in what's happening below them. Okay, so message, if I could have everyone in the world know this one thing, it would be that when volcanoes erupt, they erupt rock and gas. And I think so often in my work, I'll see people in our museum halls looking at a picture of an erupting volcano. Look at the smoke coming out of that. And in fact, my daughter, who is 6, came home just yesterday with a book from school. Mommy, there's a book in the library about volcanoes, and you study volcanoes. She was so excited to read it, and the first page said, you know, what is on fire and is emitting smoke? And then the answer was volcanoes. There's no fire and no smoke at all in volcanoes. There's nothing on fire. There's nothing burning. Okay, burning is something that happens to organic matter. Smoke is burnt residues of carbon things burning, and nothing like that is happening in volcanoes. What you're looking at here is a column of ash. It's ground up rock. It's pulverized rock. It's glass. It would cut your face to smithereens if you got hit in the face. Actually, you'd probably die of asphyxiation first, but otherwise it would be very sharp. And these are actually sometimes very large chunks of rock and ash. You see them from afar, and it does look like smoke. But this is solid material being blasted out of these volcanoes, and with them, what is propelling them is a lot of gas. So we'll talk today about what drives volcanic eruptions and why I say they're an expression of the Earth respirating. So this is a scanning electron microscope image of a piece of ash. You can see the scale bar here is 30 microns. So 30 microns is about the width of a human hair. Okay, so this is highly magnified. But you can see that it's got all these interstices and sharp. What does this look like? What are we looking at? Look at all those holes. It kind of looks organic, like maybe an ant made it, or a wasp or something, but it didn't. They're bubbles. They're bubbles. They're bubbles trapped in rock. And so while it looks like ash in your hand, it might even, at the smallest size fractions, feel like fireplace ash. It's actually ground up rock. And actually, when you grind rock up finely enough, it feels very smooth. Of course, all cosmetic products, powder your nose, you're powdering it with ground up rock, which feels very smooth. And in many parts of the world, volcanoes are a part of everyday life and common occurrence. This little boy's face has freshly blown ash, volcanic ash in it. You may be more familiar with volcanic products in the form of pumice. So if you are scrubbing calluses off your feet, the reason a pumice is sold in the drugstore, and it really is a volcanic rock. I mean, pumice sold in the store is usually natural rock that's been quarried from volcanic deposits, and the reason it takes the calluses off your skin is that it's sharp, it's glass. It's a million little micro razor blades that are polishing your skin, and that come from volcanoes. Of course, this rock and this ash and this gas can be very detrimental. So this is, I really thank Loïc for his introduction, but the Global Volcanism Program at the Smithsonian has been in operation since 1968, and I've been the director since 2010. So most of the wonderful things that make GBP the wonderful resource it is predate me. But when I became director in 2010, I became director in the same month that Eyjafjallajökull erupted in Iceland. Do you guys remember the 2010 eruption in Iceland? That's because we in the room are a lot of privileged people, largely Caucasian. Okay, Iceland, that was a small eruption. We'll learn in this talk that that was a rather small eruption that grounded air traffic across the Atlantic, causing billions of dollars in economic loss. And I became director, and my phone was ringing off the hook. I mean, you couldn't sleep. It was like ringing, the press, the media. We had to respond with video and with comments from the media and reviewing articles and things like that. And these horses are rightfully fleeing this ash because, as I said, it's carrying volcanic gas. It's a hot mix of pulverized rock without any oxygen. So it's not very good for you. And they're running away and also carrying sulfur, as we'll learn later on, that can cause immediate crop damage from essentially what becomes acid rain. This is the plume coming off the south of Iceland in this kind of what I would call a charismatic eruption, a lot of media attention. You can see the southern tip of Iceland, and this, all the bright white, you have clouds, and then this ash plume that was then billowing towards Europe. And this is an example, a very successful example of a case where we grounded air traffic. Nobody died in this eruption, okay? So a lot of people were stranded at airports, but nobody died. And what I think is really interesting from the perspective of the intersection of science and the public, or social science, is that my phone was ringing off the hook for this 2010 eruption. A few months later, in November of the same year, 2010, Merapi erupted in Indonesia. 300 people died. Thousands of people lost their homes and were permanently displaced. My phone did not ring once. Nobody contacted me. There was no media coverage, despite the fact 300 people had died, versus this eruption where there was no loss of life, but thousands of vacationing people were stranded in Charles de Gaulle Airport, the horror of it. So this was a really interesting lesson for me in the intersection of public life and science, where as someone kind of providing information about volcanoes to civil authorities and the public, my phone was ringing for the Merapi eruption in terms of the Department of Defense and the humanitarian response, but not the media. And we can kind of see this when we look at a map. This is a map created with Global Volcanism Program data. What we're looking at here is every triangle is the location of a volcano. And what you can immediately see is that these are located on margins, on plate margins. You have the west coast of the United States, the west coast of South America, Indonesia, the East African Rift, a rifting margin. And then what you don't see on here, which we don't track in the Global Volcanism Program, is the fact that most volcanoes are actually underwater, where you can't see them. We talked about this at lunch a little bit, that these are mountain ranges along the ocean floor, okay? This is called the Mid-Atlantic Ridge. It comes up here through Iceland, the East Pacific Rise, Indian Ocean ridges. These are large mountains underwater, chains of volcanoes, million volcanoes, and the crust of the earth is splitting apart, regenerating and creating new crust. So we live on this really bimodal planet where we have deep ocean basins that are young and constantly being resurfaced. New volcanic eruptions are right now, well, as we speak, volcanoes are erupting on the seafloor, generating new crust. The crust is splitting apart, transiting the ocean floor, and then subducting back down beneath the continents. And that creates volcanoes at continental margins, continental volcanoes, arc volcanoes. The reason that we have volcanoes at the mid-ocean ridges is due to the fact that the plates are being pulled apart and new material, solid earth, is rising up from a convecting solid earth. So it's hard to think about, but even though the earth is solid, it's still flowing at a very slow rate. Kind of think if you took a jar of honey and put it in your freezer upside down, eventually, you'd see flow. Don't do this in a common freezer. I suggest you try this in your own freezer, or don't do this in your mom's freezer or something. But you would get flow, even though if you cracked the honey with a hammer, it would shatter. So we do have a flowing solid mantle that melts near the surface and creates volcanoes on the seafloor. That's not why we have volcanoes here at the margins. The reason we have volcanoes here at the margins is that all this old crust is subducting down, and by the time it transits the seafloor, it's hydrated, it's full of water. And water is to rock as salt is to ice, okay? So we had some snow, right? Anyone salt or see salted sidewalk, right? The reason we put salt on the sidewalk is
melt the snow.
To melt the ice and snow, because salt lowers the melting point of ice. Water lowers the melting point of rock. It's actually exactly physically analogous. And so we get the mantle melting and we generate volcanoes where we would not otherwise because of this addition of water. What we can see here is that in terms of that, and that's governing the location of these volcanoes. Now, in addition to the location of volcanoes, you can also see I've coded the size of the volcanoes to correspond and color them according to the log population. So this is the log of the population living within 30 kilometers of an active volcano. And the thing that should just jump out at you is what? Where are all the people in volcanoes? Intermingled. Yeah. Anyone know what that is? Anyone study this area? What country we're in here? Indonesia, right? Indonesia is this like complete clash of people and volcanoes. People living on the flanks of volcanoes. That happens more in tropical regions because volcanoes create very excellent agricultural soils because volcanoes bring up enriched nutrients that allow plants to grow. So we have these really fertile soils. And in the northern climates, okay, there's a ton of volcanoes up here too, but people don't tend to live on their flanks because they're at elevation and it's cold and unpleasant. But in the tropics, you have fertile soil and warm enough conditions that people farm the flanks of volcanoes. You have a lot of people living in contact with volcanoes. So we can see that here in Central America, closer to home, in Indonesia. Here, the country with the most volcanoes more than any other country is the United States, it turns out. And that's not because of the Cascades, which most people think of. We have a lot, we own all the Aleutians. Okay, so there's a ton of volcanoes stretching out here. And you see these are all little tiny black symbols. Black is the color of the triangle when nobody lives within 30 kilometers. So that's all these volcanoes up here. But in the United States, we do have populations living in close proximity to volcanoes. Iceland is another place where a lot of people live near volcanoes. And also Africa. These East African Rift, Cameroon Line, are places where people and volcanoes are intermingled. And so there are these local hazards I talked about: acid rain, ash, pyroclastic flows, which are these, what you saw in the first couple slides, these great roiling ash and gas clouds, rock clouds that come down and kill people. But we still, yes, question.
How are you defining a volcano? Like how long is
an active volcano, right? Because you're looking and you're like, I don't remember that erupting. So at the Global Volcanism Program, we write the rules, as Loïc said. So we define, and therefore people, the community defines, an active volcano as a volcano that has had or is suspected to have had activity in the Holocene in the last 10,000 years. So a volcano that erupted 9,000 years ago is active. An example, there are tons of volcanoes that are not on this map that are co-located, okay, because the plate boundaries, you know, they're generally co-located. But if they erupted millions of years ago, I wouldn't be plotting them here. So that are Pleistocene or much older volcanoes. So these are only volcanoes that have erupted in the last 10,000 years. And what I'm telling you is that all these ridges are active today and erupting now. So those are all Holocene as well. But we don't, because we can't observe them erupt, we don't track them in our database, and that's why they don't appear as triangles on these maps. But we still care, even if no one living in the Aleutians would die of a volcanic eruption of the immediate consequences. The reason we really care about these volcanoes and their eruptive histories is what they do is disrupt air traffic, which is what we talked about initially with Eyjafjallajökull in Iceland, transatlantic air traffic. The Great Circle routes, for example, if you're traveling from San Francisco to Japan, you're going to fly, or to Hong Kong or Singapore or Indonesia, you're going to fly on a Great Circle route over the Aleutians. And what happens is that these volcanoes inject rock into the stratosphere, and that seizes jet turbines. It's essentially like putting sand in your car engine. Okay, it melts. The quartz melts, sand melts, the rock melts in the hot turbine and seizes the engine of planes, and planes fall out of the sky. And we've seen this really dramatically. KLM flight's a really great example of flights that have been grounded by volcanic eruptions. You know, all engines out. Okay, and you can have a major loss, a major loss of life, meaning the people on the plane. This is a picture. I like this picture a lot because this was taken by the crew of the space shuttle out the window of, you know, they're just floating. The volcano erupted, and the crew of the shuttle Endeavour were able to take this just like out of the porthole, if you will. But it really gives you a sense of the scale of some of these ash plumes in the stratosphere. You can see here in Russia we have a volcano erupting, and it's setting the ash plume very high in the stratosphere, okay? Okay, so how big are volcanic eruptions? We talked about Eyjafjallajökull in Iceland in 2010. And that is we give eruption sizes. This was a size 3 eruption on a logarithmic scale that goes from 0 to 9, although an 8 is the highest. You know, you always have to have a number that you didn't go to, right? So it's 0 to 9, and we have records for 8s. So Ea was like a 3 or 4. This is a 3. Mount St. Helens, yeah?
What was 8? When did it erupt?
So an 8 would have been like a Yellowstone style eruption. So these numbers are called the Volcano Explosivity Index. And so it's a little bit, a little controversial in the field because you've got two things going on when a volcano erupts. You've got the magnitude, which is defined by the volume of material that came out. So for example, you have some eruptions, like if anyone's heard of like the Deccan Traps eruption, millions and millions of cubic kilometers of magma, right? Would have a low VEI because it wasn't potentially explosive. Well, it wouldn't have a VEI at all because we only do that for Holocene volcanoes. But barring that, it wasn't explosive. And then you can have an eruption like Ea that doesn't put out very much material, but it injects it to a height. So it's a combination of injection height and volume are how we get these VEI numbers. So VEI 8s are called super volcanoes. It's like, in the movies now, you can go to a movie called Super Volcano. And there are no super volcanoes. The highest in the last 10,000 years, I believe, is a 7. So we'll talk about some of those. We'll get to those. So Mount St. Helens, do people know, who in the room, raise your hand if you remember Mount St. Helens. Right, I remember Mount St. Helens. I was a little girl at the time, but I grew up in Vermont. Mount St. Helens erupted on the west coast of the United States in Washington. But the ash, they made a big press about the ash coming all the way across the country from Mount St. Helens. And now that I teach it, I was teaching in class and no one raised their hand. And I was like, oh, I'm so old. But it was an eruption in 1980 that really changed volcanology in the United States. It injected a lot of money and interest in volcanoes in the United States because it was a very large eruption here on where people saw it erupting. So it is an order of magnitude scale. So Mount St. Helens, just to give you a sense, Mount St. Helens was a lot bigger, okay, than Eyjafjallajökull. Okay, a lot. Aya was like a 3 or 4, and Mount St. Helens was a 5. Just to give you a visual on that. Okay, you guys. All right, so let's look at some volcanoes and like how they would affect things. So when you have, here's the scale from 0 to 8, and when you have something above a 4, you can start to affect climate. When you have something above a 2 or 3, you can affect aircraft, okay? And you kind of see here the cubic kilometers of volume of material and the approximate plume heights into the atmosphere for these different eruptions. So the largest eruption in modern times is probably Mount Pinatubo. That was like a video, we had cameras, it was a news event, watch it live on TV in 1991. Here at a 5 or 6, a 6. Redoubt was another famous one in the Aleutians. And this is just coming back to that story about Merapi in Indonesia. Was not a terribly big eruption, but it was as big or bigger than the eruption in Iceland and resulted in a loss of life, but was nevertheless not a media event. Mount St. Helens and Pinatubo. So you can kind of get a sense here. This was Pinatubo, and that was a really big eruption. And then it goes bigger from there. So Krakatoa, was 1883, and we don't have any, I can't show you a picture of what the plume looked like. But this event was nonetheless impacted people living in North America. They had a year of very red sunsets that inspired, and darkness and cold. And it inspired a lot of art. A lot of people think that a lot of the more macabre art created in this time period was in response to the way the atmosphere changed in response to an eruption that was, a magnitude 7 or 8. And so, of course, this is The Scream by Edmund Monk. Yes?
Didn't they also record the sound of the explosion though? And that's the biggest sound ever recorded?
Oh, I don't know.
Yeah, because I saw that in a documentary. So the
true.
sound actually traveled around the globe.
Yeah.
And it was the biggest measurement for a sound that has ever
From
been
Krakatoa,
measured.
yeah? Yeah, it was definitely an enormous eruption during historical times. And would have been loud and changed things as far on the other side of the globe. And right, so what would be a 7, something like Toba, and what I'm going to come back to are some of these climate changing eruptions. Okay, so volcanic eruptions, they explode because of trapped gas. So you can go and buy a volcano kit. When you go to Walmart and buy a volcano kit, which is usually made by the Smithsonian, and so I definitely suggest you do go buy a volcano kit because it definitely supports my program. They actually are not accurate physical models of volcanoes at all, because volcano kits work by having a chemical reaction that causes like a bubbling and fizzing. But that's not how real volcanoes work. Real volcanoes work identically to seltzer water. Okay, so we all have experience with seltzer water. We have a liquid here, that's the magma, and it has carbon dioxide dissolved inside, just like magma. It's CO2 in both cases, okay? And in volcanoes, we'll learn that it's water vapor. In this case, we have CO2 in liquid magma. And it's dissolved in there, and why? Why is it dissolved in there? Why don't I see any CO2 bubbles? Pressure. Pressure is holding the gas dissolved in the water. The CO2 is now dissolved in the water due to the pressure. If I then cause an eruption, you can look closely here, and you see bubbles nucleating inside the water and rising to the top energetically and buoyantly. It's boiling, okay? The water's boiling, okay? It's dissolving CO2. This is exactly how a volcano works, all right? The magma has dissolved water and dissolved CO2, and when the pressure is released on the volcano, what happened in Mount St. Helens is you had a landslide that suddenly released the pressure on the magma chamber, The pressure was released, all the gas that I want out of this magma, exhaled into bubbles. The bubbles rose because they were buoyant energetically, and the magma just comes along. Just like the water just came along for the ride. It's the gas trying to escape, and the magma comes along for the ride, just like the water. And if I had forgotten my water bottle, we would have talked about this with a still photograph. So, what gases come out of volcanoes? Mostly water, okay? Water, carbon dioxide, some sulfur dioxide, and then a bunch of other halogens and other boutique gases, okay? These are the percentages. You can again see it's mostly water. Sulfur is a really important one, though. Not because it's large on a mass basis, but because we can image it, okay? Sulfur has really low background in our atmosphere. The atmosphere is full of water vapor and carbon dioxide, but it doesn't have that much sulfur dioxide, okay? So when we look in the UV, we can see sulfur showing up really well. And here's a visible photograph of a volcanic plume, which, is it smoke?
No.
Volcanic gases and ash, okay, in this case probably just steam, and SO2, which you can see with a UV camera. And this is really important in the study of volcanic gases because this is the only one that we can really easily image. We can't, other than in the visible, of seeing that steam in the visible, we can't see it easily with other technologies. This is, sulfur is kind of an important gas also because we talked about acid rain. It also creates volcanic smog, or if you live there, they call it fog. In Hawaii, if you're in Honolulu, you can get, fog. You get a kind of hazy, misty day. I wish I had I don't think I have in this presentation, but you can see great pictures of it. It kind of looks like LA. It looks like pollution, but it's volcanic gas instead. And when we look at, for example, in Tambora, which is like one of these very large eruptions, as you saw in your documentary, it's like a super volcano-sized eruption. It actually changed climate in Europe. Now, we said water and CO2. So what does your gut tell you about the way climate changes?
Warm.
Warm. Yeah, because water and CO2 are greenhouse gases. And you would be wrong. And that's because water and CO2 do come out of volcanoes, but the amount of CO2 that, for example, and this it played an important climate feedback before humans. Now, we so dominate the signal, okay, by a factor of like the anthropogenic effect over the volcanic effect is about 150 times. So we're well over 2 orders of magnitude more important to CO2 in the atmosphere than volcanoes now. People are burning fossil fuels. So what happens when you have a volcanic eruption is that you put ash and you put sulfur aerosols into the atmosphere that block the sun. And they block the sun and also absorb radiation and have a cooling effect on the planet. So in the summer of 1816, after the 1815 eruption of Tambora, the canals were frozen in August and July. There was famine, there was crop failure, it was snowing in July in France, okay, and in August. And that's all because of the cooling effect of a volcano erupting on the other side of the globe. Okay, so these are global climate effects. They are relatively short-lived, a number of years, and the effect is to cool, not to warm, though the longer-term climate moderation due to CO2 and other things might have been more complicated, but in a way we don't understand as well.
Can I just ask, where is Tambora, or where did that?
Indonesia again. It's always the answer on any exam that you ever get, like from Loïc. If you don't, it's Indonesia. Just like, where is this fucking Indonesia? It's kind of like if you took like art history. Like, where is this church? France. I mean, if you don't know, and you just like need to throw something out there, Indonesia. So we've seen pictures of temperature and images of SO2. Okay, what about CO2? Now this gets a little bit more into my own research on volcanic gas emissions. Carbon is so important. It's the building block of life. How many people here feel like in some vague way they're studying the carbon cycle? Right? There's a lot. You're all environmental, right? You're all studying the carbon cycle at some point, right? And that's the superficial carbon cycle. But 98% of Earth's carbon, if you had lunch with me today, is located where?
In the mantle.
Mantle. Of course, yeah. I paid attention to this. It's the interior of the Earth is just so big that even if it only has like a little bit of something, it still completely dominates the global budget. Okay, so most of the carbon is on the inside of the planet. The scum on the surface is just like, it's like the burp at the end of a meal. It's all inside the Earth. Okay, but we can't image it easily because of this huge global atmospheric background due to anthropogenic emissions. So raise your hand if you're familiar with this figure. Yes, probably most of the room has seen this figure. This is the famous Mauna Loa CO2 monitoring that began in the 50s, and we see it going up and up and up. Today, I think like last year we exceeded, or 2 years ago we exceeded 400 parts per million. And this makes it impossible, or not impossible, but nearly has been impossible to see volcanic CO2 because of this high background. But the Global Volcanism Program has an initiative to incorporate emissions information about volcanic gases into what has otherwise been a physical volcanology database. So this is Skiamaki, which sadly stopped, it's now space junk, but was a satellite returning data to the Earth between 2002 and 2012, and it's UV satellite, and it can detect CO2. So what we did is we looked at, a postdoc in my group named Christoph Popp, who's an atmospheric chemist, wonderful, brilliant scientist who didn't know much about volcanoes when he came, but we were like, oh, it's okay, we'll tell you about the volcanoes. We know where the volcanoes are. And he looked at satellite retrievals in the UV for CO2, and we decided to look out here in the Aleutians at the 2008 eruption of Krakatoa, and Krakatoa is out here. Now, this volcano is so remote, these volcanoes are not instrumented. There's no one standing out here. Okay, think like here's the United States and here's the Aleutians, right? There, as we saw previously, there's no one living out there. No one out there with a UV camera, right? And even after the eruption, here's a picture from August 28th, which is a couple weeks after the eruption happened, that like a person actually was there to take a picture, right? On the some kind of ship out there. So here's Krakatoa, this little triangle, all right? And this picture is from August 13th, okay, like a week later, and everything you see here is SO2 that came out of the volcano. So you can see that while this volcano is out in the Aleutian Islands, some of this plume material might have passed right over your heads, right? And certainly in a big swath that basically completely covered North America and swirled about here. So what Christoph did in my group that was so brilliant was he said, okay, we can see the SO2. We know where that is. It's really easy to see volcanic SO2 because there are no other, or very few, or at least if there are other SO2 sources, we know where they are, like smelting and things like that, right? So we'll say that wherever the SO2 went, that's the volcanic plume. And then he looked at the pixels, the retrievals, and defined the SO2 plume as anywhere that a pixel had greater than 1.5 Dobson units of SO2. It's not important what Dobson units are, but it's kind of an integrated column density of that gas. He said that's the plume. Now let's define those pixels as the plume, and let's compare the CO2 of those pixels that we measure with pixels that did not have elevated SO2. Let's just look at the plume pixels and see what their CO2 was. And he was able to produce, we think is the first ever map of volcanic CO2 from this eruption, and estimate that the volcano emitted somewhere maybe between, best estimate, 12 to 50 teragrams of CO2 in a single eruption. Now I just saw you go, 12 to 50 teragrams. It sounds bad, but New York City puts out about 50 teragrams every, anyone want to fill in?
3 hours.
Every day. New York City produces about 50 teragrams of carbon every day. So this volcano in whatever, a day produced like a New York City amount of CO2, which I think it's a really open question about what the CO2 flux from the Earth's interior to the atmosphere is via explosive eruptions. We really don't know because we don't have any data. And so this is I'm now going to show you a forward model. It's called a high split model of the plume. This is an injection, a simulated injection of 150 teragrams of CO2 into the atmosphere at Krakatoa, using what is known from meteorological data about how that air mass would move. If you had a point source of CO2 at the location of Krakatoa, injected that into the atmosphere, and followed air currents, where would that CO2 go? And I'm hoping it looks similar at the, to the SO2 picture you saw, right? So it's we think a good demonstration of being able to image CO2 for the first time. And so I want to share with you the GDP website as a resource in your research or in just for fun. Caitlin takes pictures of ants for fun. You might be interested in volcanoes for fun. The GDP program, as I said, has been in existence since 1968, and what we do is we record eruptions. Okay, so every time from big eruptions like Pinatubo to like a volcano in the middle of the Pacific Ocean that nobody cares about, and it's a tool for research. It's a tool for civil authorities in hazards mitigation and in basic research, and for the public to learn about volcanoes. And so there's in 2013 we launched a new version of our website that has our database available for download for the first time in the program's history. You can now do smart queries of the database and look at what's erupting near you, which in this case the answer is nothing. But if you were taking a vacation to the Caribbean and were interested in volcanoes there of Central America, you could find a lot of great information online. And so I wanted to close my formal remarks by thanking Christoph, who is leading the research on volcanic CO2, Brendan McCormick, another postdoc working on SO2 in our group, and the GDP staff. And what I have after this is a lot of information more about my own research and going to sea and getting samples from underwater volcanoes. But since I've talked at you for 35 minutes, I would take questions before further taking your time.